So after seeing the PV modules, yes, now we continue exploring the other elements in a PV system, okay? The storage, batteries, the power conditioning, okay? We were introduced about storage and power conditioning on Wednesday with a roundtable we had, yes, with our colleagues from Studer, from Ferntech, and from Inventus Power, okay? I'm going to go a little bit deeper, some details of these components, okay? First of all, to understand the components, let's recap a little bit on the configurations, yes, that I presented in the overview the first day. PV panels are very flexible, very adaptive. We have many applications, and essentially we have off-grid PV systems, but also grid-connected PV systems. The off-grid PV systems will rely on the presence of batteries, normally. Grid-connected PV systems will need the branching onto a distribution grid, okay? And then we have hybrid systems that can combine different generation options or different distribution options. Okay. Some examples. We will come back to this when we do exercises for design, yes? This is a project I worked in for rural communities. We have solar home systems, yes? We can see here PV panels on the roof, and then inside the house, we can see here a charge controller and the battery. And you can see, yeah, the battery is in the middle of the kitchen of the house, no protection. Yes, very dangerous to have the battery like this, yeah, with the children around, etc. But this is very typical situation in rural areas with solar home systems. Okay, still off-grid systems, individual PV systems, but a bit more, yeah, with a higher capability. They can incorporate better because they will be consuming AC current, yes, to power TVs, computers, refrigerators, fan, etc. AC loads, okay, appliances. We also discussed about mini grids, yeah, another type of configuration where we have different users, yeah, residential users, commercial users, could be industrial users sharing together, okay, a low voltage grid. I was saying that in all these configurations, the PV module is very much the same, yeah, very similar modules, but we can see a lot of differences in the power conditioning elements. The batteries, the charge controllers are different, okay? In the next session we will have on Wednesday, we will be discussing in detail the case of the interconnection of mini grids. That is another configuration, okay? Where you can imagine a community, a rural community that have eventually they have mini grids for each community, and at some point the grid arrives, or the grid is not far from these communities. These communities could connect their mini grid to the grid. That's one option. But another option is that two communities, they share one same mini grid. Okay, that's also another configuration possible. Why not? And then why not this shared mini grid can also connect to the grid, okay? So all of these configurations, this is another example, yeah, in a small system, grid connected, yeah, or self-generation. In all these configurations, the important elements to look at are the power conditioning, and at some point the batteries. Okay, this is what really makes these elements are what are going to make possible one configuration or another, rather than the PV panels. The PV panels are more or less the same in all configurations. Okay. In grid-connected applications, we can even consider the incorporation of batteries. Yes, we could. Would be interesting to have a battery. Yes, batteries could help if we have availability of space, and batteries could also help in increasing the self-generation rate. Yes, in a condition where the grid supply is not good, we have frequent blackouts. Yes, we have frequent cuts of the service, and or the cost of the electricity from the grid is very high. Yes, so then we can think of having batteries even if the PV system is connected to the grid. Okay. Typical configuration of a large scale, PV park or PV farm, where we can see again the central role of inverters. You can see the generation, the PV modules, junctions, protections, and then the inverters. Okay, transformer and connection to the grid. So let's have a look at storage, at the batteries. Okay, very important element of PV systems, typically found in off-grid applications, but also sometimes in grid-connected applications. So batteries, what is a battery? I think here in these sessions, in this room, are familiar with batteries. Batteries store electricity, okay? And they have different purposes, okay? For off-grid applications, what we want batteries to do is to supply instantaneous power, that has to be higher than the solar, that could be higher than the power supplied by the solar modules, okay? So batteries not only store electricity, but can also give us higher power availability than the power that the PV modules are generating, okay? Pablo from Studer, engineer Pablo Munoz from Studer on Wednesday mentioned this possibility, as one of the reasons why we use DC coupling in mini grids, okay? At the same time, the batteries, they help to keep the voltage stable, all right? Because the voltage of a battery is stable, more stable than the voltage in a PV module. Remember, the PV module will be working in the IV curve, okay? It can have some fluctuations, all right? And of course, the batteries, they will give us electricity when there is no sun, okay? Under cloudy moments, at night, etc. But also, batteries, they have a meaning, they have a sense, make sense in some grid-connected applications. In small grid-connected applications, like residential or commercial or even public buildings, the batteries, as I mentioned, they will help us to increase the solar fraction, okay? The self-generation ratio, the amount of electricity that we obtain from the sun, okay? That is important every time we think of projects that we want to do that have a, sorry, Dr. Lucas, hola. Yes. Okay.
Yeah, we can continue now.
All right. So batteries have also applications in grid-connected configurations, okay? For small to medium PV systems, they are helpful in increasing the solar fraction and the self-generation ratio, but also in large PV farms, utility scale configurations. Batteries are very much used and of interest because they facilitate the integration of the renewable energy generation. Yes, the batteries help smoothening, yeah, the output of the PV plant, okay, and they can help in the response and the ramp up situation in the power. They can smoothen the power curtailment. They can enable spinning reserve, etc. Okay, and batteries are flexible, are fast responding elements that help to stabilize and then guarantee the reliability of the grid. Okay, they are used in strategies for frequency regulation and voltage control. Okay, especially when there are sudden changes. Imagine a PV farm in a cloud. Okay, then you could have an instantaneous or very quickly a drop in the power generation from the PV panels if a cloud comes, and you could have, imagine, half of your power being cut because of the cloud. If you don't have a battery that can smoothen this effect on the grid, that could create problems. Yeah. Okay. And the use of batteries, apart from off-grid applications where we need batteries to supply electricity when there is no solar generation. Even in the case of grid-connected applications, batteries have a use. Okay, and I was mentioning that even in the case of PV farms of large-scale PV systems connected to the grid, yeah, power plants, batteries are very much being in use. To facilitate the integration of the solar generation into the grid, and to also for a number of ancillary services to support the grid, and also to allow to help and maintain the stability and the reliability of the grid system, okay, in terms of frequency control, voltage control, frequency regulation, especially when there are sudden changes in the solar generation. Okay, so if you remember, engineer Santiago Antolin showed this picture from Inventus Power. What is a battery? So essentially, we have similarities with the PV cell because, again, we have a flow of current from a flow of electrons from a negative electrode called the anode to a positive electrode called the cathode. The cathode in the case of battery. Again, in direct current, in DC. And if we put in contact, if we bypass the positive cathode electrode with a negative electrode, the anode, we will create a short circuit. This is the flow of electricity. This is like in the same picture we have here if there wasn't the load. So types of batteries. They were briefly mentioned by engineer Antolin. We have the lead-acid batteries, which are the most commonly used batteries for solar applications. Hello, we have a new person in the call. Okay. Perfect. If you can mute yourself, thank you. Thank you very much. Let's continue. Then, apart from lead-acid batteries, we have lithium batteries, lithium-ion batteries, which are at the moment becoming they are the standard for electromobility, and technology getting a lot of maturity in the recent years, and also having an increasing penetration in the solar PV systems markets, especially at the moment for grid-connected applications. both at a large scale and small scale, domestic, commercial. Okay. But also we have other types of batteries, alkaline, nickel cadmium, nickel metal hydride, batteries that are either too expensive or they have issues with the toxicity of the materials. In case of the nickel cadmium, for instance, heavy metals, that make these batteries not really suitable for solar applications. They are mostly used for power electronics, machinery or solutions or products, but not really for solar applications. For solar applications, we mostly concentrate on the lead acid type of batteries or the lithium ion. Okay, so in lead acid batteries, typical, shapes, forms where they are very familiar to us. In a casing, we have different cells. Typically, this is a picture of what could be a monoblock battery, giving a total of 6 volts eventually, or 12 volts, yeah, composed of different cells that will be giving normally 2 volts per cell, okay? And each cell is separated from the neighbor with a divider, with an insulator material, okay? And then each cell is composed by different plates, all the electrodes, and the whole battery is floated in this case, or is swimming, let's say, in an electrolyte solution that was introduced in this slide mentioned by engineer Antolin on Wednesday. Electrolyte is a dilution of water with sulfuric acid. This is why we call these batteries lead acid, because the plates in the electrodes are made of lead dioxide, the cathode, and solid lead in the anode. Okay, so this is the lead acid batteries. Types of lead acid batteries that we have. Okay, the starting batteries, as we call them, they are designed to start engines, typically found, yes, in small vehicles. They are designed to start engines, so they are designed so that they can deliver a big small solar application. Okay, solar application, we want basically the other way around, probably not so much power or instantaneous power or current, but we want it for a number of hours. Yes, in off-grid applications, we would probably like to have electricity service throughout the night. Yeah, so that's at least 6 to 8 hours. So this type of batteries are not really recommended for solar systems. Okay, when we do our specifications for our projects, for our programs, we have to make this very clear. Well, these batteries, they are not designed then for deep discharge. Only 5% of the capacity should be discharged. Yeah, and they very quickly decay. They age very quickly if we go for deeper discharges. In any case, they are not really recommended for solar systems. I know they are used for solar systems, especially for solar home systems, lots of and they have to be cheered. Batteries, what we call the traction deep cycle batteries. Okay, in this case, these batteries are designed to power electric vehicles, not just the starting of a combustion-based gasoline or diesel engine. Electric vehicles where they need a continuous supply of electricity, forklifts, all types of machineries. In this case, they have normally more robust plates, and they are designed for more continuous delivery of power. And they can also be discharged deeper, down to 80% of its capacity. So this makes them a bit more convenient, okay, for solar applications, even though they are not ideal, okay, because the number of discharge and recharge cycles is not very high. They will not last very long, but they are cheaper than what we call the solar batteries, okay? So they could be an option. They could be an option if there are some restrictions in the project, cost restrictions, availability in the suppliers, etc. So this could be accepted, but under the consciousness that the operational lifetime of these batteries is not going to be as good as what we call the flooded batteries or the solar quality batteries, okay? Normally, when we refer to lead acid batteries in the solar sector, we implicitly mean this type of batteries, okay, where they are flat plate or tubular plate, but this kind of deep cycle, yeah, stationary batteries, okay. This type of batteries essentially can be of two manufacturing, let's say, arrangements, what we call the sealed or the vented ones, okay? The sealed batteries are the ones that are completely closed. The vented are the ones that we can access, yeah, the electrolyte, the deposit, the chamber of the battery, we can actually access. These examples here, you can see there's a little cap here, there's a little lid that can be taken out. So this has advantages and disadvantages. The advantage is that we can top it up, the electrolyte when necessary, so these batteries can give higher performance than the sealed ones. But at the same time, if we can access the electrolyte, we can access the acid. So this can be toxic and dangerous. So we have to think about who's going to do the maintenance of these batteries, under which conditions, etc. Health and safety aspects are very important. Yes, and remember, these batteries can discharge large amounts of currents. I'm talking about currents in DC that can reach 50 amps, 100 amps, or even more. Yeah, that's a lot of current in DC. Very serious danger, conditions. Very, very dangerous conditions for manipulation by people that are not trained in electricity systems or are not conscious, okay, of the risks. So be careful with these batteries. Flooded batteries with vented cells, we call them VLA, vented lead acid batteries, or also the flooded lead acid batteries. You can see them as VLA or FLA typically. Normally made of tubular plates, yeah, for the cathode and the anode. It's how do you call it? An alloy, yeah, of lead and antimony. And the electrolyte is in liquid form, okay, and the cells, the battery cells, are open. I mean, they are closed with a cap, but they can be opened, and in a way they allow the vapors that generate when the batteries are charging, mostly hydrogen vapor. It is allowed to evacuate, yes, when the battery reaches the high or the charging voltage levels. So there is a certain loss of oxygen, of hydrogen ions that needs to be replaced by adding water, distilled water, pure water, not mineral water, okay, distilled water to top up the level of the electrolyte, because the acid will stay, but the water, some of it will have evaporated, okay? So when these batteries are charged, the specific gravity, density of the electrolyte is around 1.24 because it's a mixture of acid and water, and the density, instead of being 1 for the water, is 1.24. Okay, so there's a lot of presence in small acid, in the sulfuric acid in the electrolyte. Okay, so refill with distilled water and not with mineral water. Another issue, you will find these batteries noted with the standard code of OPZS. That is the acronym for some German words, which means stationary, Panzerplatte, tubular plate, flüssig, or floated batteries. So, and whenever we see the OPZS, the S is the important letter here. This is a floated battery, the one that needs to be topped up with distilled water. So, bottom line, when we do a project with this kind of batteries, we always have to remember to think about the procurement of distilled water. Okay, where are we going to get the distilled water from? Distilled water sometimes is not that easily, readily available in remote areas. Okay, the other type of lead acid batteries most commonly found in solar projects are the sealed batteries, known as SLA or valve-regulated lead acid batteries, the VRLA. These are also known or sold as maintenance-free, okay, batteries. And the electrolyte is in a solidified form, in the form of a gel, normally. Could be in gel or in AGM, in absorbed glass mat form, a bit more complex electrolyte, or a mixture of both. These batteries are referenced with the OPZV code. Again, as opposed to the OPZS, we have the OPZV. And in this case, the V stands for verschlossen, which means closed in German. Okay, so these are closed batteries. We cannot access the battery cell, the electrolyte. This makes these batteries safer, easier to handle, but they have a little bit less of performance, of efficiency than the OPZS. Yeah. So this is again the pros and cons of choosing equipment. In this case, performance versus safety, okay, or easy to maintain. Okay, very quickly, what happens inside a battery? We have a chemical reaction. Engineer Antolin told us, yeah. So essentially, in the process of charging, what we have, or when, let's start by saying that when the battery is completely charged, what we have is that the positive electrode, the cathode, has a deposit of lead dioxide, okay? Is this case here. So the anode is completely full with lead dioxide. It's made of lead dioxide, and in the negative electrode we have only lead. Okay, this is the case. This is a situation with a charged battery, and the electrolyte will have high density, a lot of acid in the electrolyte. When the battery is discharged, we have part of the acid, yeah, that dissociated, and the sulfuric ions they react and they deposit in the anode. So this plate then converts or starts the formation of lead sulfate, okay, in both electrodes actually. Okay, so when we discharge the battery, what happens in chemical terms is that the electrolyte dissociates. There's less acid in the electrolyte, so it's mostly water. Okay, and these sulfuric ions, they start depositing in the plates. Okay, when the battery is recharged with the entrance of the provision of supply of electricity to the battery, what happens is that the lead sulfate crystals that are deposited in the plates, they break down and they dissolve again. okay, going back into the liquid form and the mixture with water, okay? And in this process, there's a bit of a release of hydrogen gas and oxygen too, okay? So we can, apart from controlling the voltage, another way of knowing if a battery, if it's a vented, an open battery, a flooded battery, if it's charged or not, is by measuring the density of the electrolyte. If it's a high density, a lot of acid in the electrolyte, the battery is charged. If the electrolyte has low density, little quantity of acid, then means that the battery is mostly discharged or at a low state of charge. Okay, so the control of the specific gravity is one of the parameters that we can use to know if a battery is charged or not charged, okay? Of course, that is when we can access the electrolyte, but if we are using sealed, maintenance-free batteries, we cannot access the electrolyte. So in those cases, we can only measure the voltage, the open circuit voltage of the battery, to see if that battery is charged or not charged. But the specific gravity of the acid is a more precise measurement of the condition of the battery than the voltage. Okay, very quickly, what happens when a battery charges? Typically, we have three stages, what we call the bulk charge. It's stage number 1. The second charge is the absorption charge, and the absorption stage, and the third stage is the floating stage, finishing at the equalization point. In the bulk charge, basically what happens is that batteries, they are charged at a constant current, okay? They demand a constant current, and the voltage rises, okay? In this chart, we can see the current and the voltage. In the bulk charge, we have a constant current, and little by little, the voltage rises. This nominal cell, a typical battery cell, rated voltage around 2 volts. So we can see here that when the battery is getting charged, the voltage rises until it gets to a certain level, what we call the absorption level. In there, little by little, the current starts to be limited. This is the ideal charging mechanism or charging method procedure for a lead acid battery. In the absorption stage, what we want is to keep the voltage stable, and little by little we can afford to start decreasing the current, okay? So we can start in a way like cutting off the current going into the battery, okay? We will see that later on. The component that will do that is the charge controller, all right? And then when we get to the end of this phase, then we can say that this battery is floating or being kept at the floating conditions, which means that its voltage is kept between a threshold, or maximum floating and minimum floating voltage for that particular battery. So the set points, the thresholds of when the battery is at absorption stage and when it is at equalization stage, these thresholds are defined by the manufacturer of the battery. So this information has to be in the technical specifications of the battery we choose, because we will need to adjust the set points of the charge controller to be able to operate with the convenient voltage set points that every battery needs, okay? Another important aspect of batteries is the capacity, okay? So the measurement batteries are like a deposit, like a tank of electricity, of energy. So we can size batteries by the energy we want them to store, okay? That is units of energy, so kilowatt hour, okay? But we have to be aware of one very important condition, aspect of batteries, of lead acid batteries, is that the amount of current that we draw out of a battery will condition how long this battery will be able to deliver this current we are drawing out of the battery. That is expressed in the parameter of the capacity of the battery. Okay, so the capacity of the battery is expressed in amp hour. This is telling us the amount of time a battery can deliver a certain current. Okay. For how long? So a battery that, for instance, a battery that is rated on a capacity of 100 amp hour, this would mean that it can give us 1 amp during 100 hours, okay? Or can give us 10 amps during 10 hours, okay? So it's a combination of the current that it will give us and the time during which this battery can give this power. Now, the situation is that batteries, this factor, the capacity, is not proportional, is not constant. The capacity, it depends on the current that we actually will be drawing out of the battery, okay? So meaning that one battery, for instance, if it is rated at 100 amp hour to be discharged in 10 hours, that same battery, when it is discharged during over a longer time period, it will give us more than 100 amp hours. Okay, in this case, 100 amp hours battery during 10 hours, same battery can give us 150 amp hours if it is discharged in 100 hours. Okay, so the bottom line here is that the capacity of a battery is not constant. It depends on the rate of discharge. If we have a fast discharge, less energy can be obtained. And if we have slow discharge, more energy can be obtained. Okay, and the critical factor here is the current at which we discharge the battery. All right, we all have domestic examples of that. You can have old dry cell batteries that are not good enough for a certain appliance that requires, I don't know, kind of toy or something that moves. But when you put it in a radio, it's still working. So that's exactly the same case. Dry cell battery in a radio consumes very little amperage, very little current. So it can still deliver energy. Whereas if we ask this same dry cell to power a moving machine or a moving toy, whatever, we will see that it's not working. The battery doesn't have the capacity to deliver high current anymore. In the lab, we get this kind of curves. You see, this is one same battery, the voltage and the discharging time. This is logarithmic scale, yeah? So when we discharge this battery in 5 hours, so very quick discharge, very high current, okay, almost 9 amps. After 5 hours of discharge, then the voltage drops, boom, and the battery is discharged. No more energy can be drawn out. But the same battery, if we discharge it over a very long time, 100 hours, okay? Of course, discharging it over 100 hours means drawing smaller current from it. Instead of 9.9 amps, we only draw 1.1 amp current. Then, after 100 hours, then the voltage will drop. And the capacity if we take into account the amount of hours, 100, and the current at which it was discharged, this capacity is 110 amp hours compared to the capacity found in that same battery when discharged in just 10 hours. Okay? There is an equation that relates these changes. That's called the Purkett's law, which is used to regulate and relate the change in capacity in lead-acid batteries. Okay, typically this Purkett constant is rated as 1.1 to 1.5 in lead-acid batteries. Okay, and this is the formula. If we know the capacity of a battery, the capacity 100 hours discharge rate, this is the formula we can use to know what will be the discharge time if we apply whatever discharge current in a battery. Okay, so if we know the Purkett constant for that particular battery, each battery will have specific constant. Okay, even from one same manufacturer, because this constant depends on how the battery is manufactured, etc. It will be between 1 and 1.5 for lead acid. So this expression will can help us to relate the capacity. Okay. Now, how do we size batteries? Lead acid. These are simplified sizing equations, but I think they're very useful when we think about off-grid PV power systems. So the energy we want to store in a battery is calculated as the energy that we need to deliver from the battery every day times the days of autonomy. This is a parameter used in in backup applications or off-grid applications. That will be the number of days that this battery can supply electricity, even if it's not recharged. Okay, and that divided, of course, by the maximum depth of discharge of the battery. Remember what engineer Antolin told us: lead-acid batteries typically admit a depth of discharge up to 50 or 60%. Yeah, lithium-ion batteries, they admit depths of discharges that go well above that, down to or up to 80-90%. So this is the formula we will use to estimate, to calculate the energy to be stored in a battery. Now, for the capacity, we need to relate the energy stored in the battery with the voltage at which this battery will be working. Yeah, typically rated voltages for batteries: 12 volts, 24, 48. Okay, in DC. And then that will be the capacity in 20 hours of discharge, because that's more or less a daily cycle. Okay, 20 hours of discharge. If we want to know the capacity over 100 hours of discharge by using the Purkett's law, and this is a simplification, yeah, but it's a good rule of thumb to convert the capacity 100 hours of discharge to the capacity of 20 hours of discharge. You can use a factor of 1.2. This is important because when you buy batteries or when you check batteries from manufacturers, you need to make sure which is the capacity you are talking about. Okay. Following our example from Gurue, yeah, where we want to consume 10 kilowatt hours a day. So this is an example how to size a battery, yeah, for Gurue. I'm using in this example 3 days of autonomy, considering that we want a battery that can be there for 3 days, can store the energy for 3 days. It's a lead acid battery, so a maximum depth of discharge of 50%, okay? That will give us a reference for the energy to store of 60 kilowatt hour, okay? Now, if I choose this battery to work at 48 nominal voltage, that gives me a battery capacity in a daily period. So discharge, maximum discharge time around 20 hours, okay, of 1,250 amp hours, okay? So that's our example in Gurue. Remember, example in Gurue, we're talking about PV module size, PV array size of 2,700 watt peak. We saw earlier on that we would need roughly 17 square meters to install the modules. Now we know we would need about 1,250 amps hour of battery capacity for lead acid. Okay. So let's do a bit of an exercise with this. Okay, quick one, simple one. Here I'm sharing with you what is the catalog of OPZ-V range of batteries from a very good manufacturer from Canada and UK, which is called Rolls, Rolls batteries. And in here we can see the catalog of batteries they have. Now, in here we have calculated that we need a battery with a capacity 1,250. My question to you now is, which of these batteries are we going to choose? Are we going to choose this model here, A, or this one here, B, or this one here, C? Which one? I'm asking you, which one do we choose? Which one would you choose? A, B, or C?
A pergunta é para todos os colegas. There is the answer C.
C.
Answer C. Anybody else? Any other opinion? No other opinions? Yeah, Carlos? No other opinions, right?
No more opinion.
Okay, good. Yes, this is correct, yeah? We want to have 1,250 of capacity, but in C20, okay? So obviously we need to check the C20 column, yes? And not the C10 or the C100. Because you see, these are models of batteries, and the capacity they have is different if we discharge them in 10 hours, 20 hours, or 100 hours. And the difference is quite substantial. Yeah, the difference is quite substantial. This battery here, the first one, it will give you 301 amp hour if discharged in 100 hours, but it will give you only 224 amp hours if discharged in 10 hours. Okay. Also, let's look at the weight. Remember what engineer Antolin told us about the example in Mali. Yeah, the logistics, how to carry all this weight to remote sites. The choice of a battery versus another. Every time you go for bigger models, there's a lot of weight. 95 kilos each battery module. Okay, that's a lot of weight. Okay. Yeah, I was saying that I'm using 50% of depth of discharge, as the maximum, because it's a lead acid battery. If I was using a lithium ion battery, I could put here 0.9, 90%. Okay. Was that the question, or also for the table? Is that okay? Can I continue? Yes, shall we continue then?
Yes, clear.
Sorry? Yeah, it seems that now it's clear, Paul.
Ah, okay. Thank you.
It seems that it's clear now.
Good.
It's clear in terms of the explanation for the example.
Right.
So now let's go to the table.
Ah, the table. Okay. Okay. So we have this figure here, 1,250 in a capacity C20. So we look in this column here, the C20, yeah? The capacity, the discharge time, 20 hours. And then we look at which is the model that will give me 1,250 amps hour in a discharge time of 20 hours. And we can see it is here, this one, okay? Because we are looking at C20. So it is letter C, this one. Because this one, A, it's too small. It will not give you 1,250. Okay, it would give you 1,250 if the capacity was C100. But our calculation was not C100, was C20. All right. So because it's C20, what we are calculating.
No, we can pass them. I'm clear.
Exactly. You go for the next model. Okay.
Now it's clear. We can pass. Sorry.
And if we had looked at it from the C10 point of view, then we would have needed the following model. Okay. Okay. So when we choose batteries, we have to take into account the capacity calculation. And the depth of discharge, as you were asking, of course, is very important because it will give you one number or another. Okay. Okay, the temperatures. The temperature is very important. It affects the performance of a lead-acid battery. Yeah. When the temperature is very high, above 35 degrees Celsius, it can start to be harmful for the battery. Okay. And even higher, 55 degrees, then the electrolyte can get something somewhere closer to, not to boil, but very warm. And then it can also destroy the battery, yeah? Even the separator of the cells, all right? At the same time, if the temperature goes very low, yeah, the state of charge of the battery, the voltage, decreases very, very quickly, okay? All right, in terms of the lifespan, okay, we talk in batteries, we talk about the number of cycles, okay? So the life of a battery is graded or rated in number of cycles, okay, which will be limited, okay? Charging of the battery is reversible, but it cannot be done forever. So there's a maximum number of cycles, charge and discharge, all right, that can be done, okay? desulfation, that is the deposition, yes, of sulfate. Remember when the ion SO4 ions, yeah, when the sulfuric ions are deposited in the plates. Hello. Okay. Oh, you cannot hear me? The audio is bad today, yeah? All right.
I'm still here, but I don't see anyone else.
Yeah, I'm here, yes. It looks like they are down again. Yeah, they are down. You're out, huh? You're out of the call. Hey. I don't know, Carlos, perhaps, I don't know if this is uncomfortable, yeah, for the attendees to follow the talk, then we can stop here and then we continue in the next session. Because I don't know, I fear that they might not be they might not be following, yeah, with the constant interruption. You can hear me?
Yeah, but we can hear you now in the room. Yes,
okay.
In the room,
we have. When are we going to close today? 5?
No, 4:45.
So we have another 15 minutes, yeah?
15 minutes, yes.
Okay, so let me finish with the batteries and then we leave the power conditioning for another moment. Perhaps we can schedule something for Tuesday.
All right.
Okay, we'll talk about it after. Okay.
Yeah.
Okay, let me finish with the batteries then. Okay, thanks. Okay, so seems like you are back, yeah? Good. Let's finish with the batteries. So basically, the primary cause of premature battery aging and eventually failure is the deposition, yeah, of the phosphate ions in the lead. Sorry, the sulfate ions in the lead plates. That's this is the phenomenon we know as sulfation, yeah. So that is the great danger of lead acid batteries. That in effective terms, what happens is that those sulfate ions, they cannot be dissolved again in the electrolyte. Remember, when the battery is charged, means that there's a lot of acid in the electrolyte. Okay, and when it is discharged, there's little acid because the sulfate ions are stuck onto the plates. Okay. So that's a problem with lead acid batteries if they are discharged too deep, for instance, or if they are not recharged after a long time of being discharged. Okay. So some references on the lifespan of batteries in number of cycles of charge and discharge. Yeah, and the maximum depth of discharge down to 80%, but that's really very, 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 very deep discharge. I don't recommend to go down to 80%. I stick to what engineer Antolin from Inventus told us. Yeah, he works for a battery manufacturer, and he recommended 50%, if you remember. Yeah. So 50, 60, eventually deep discharge for a particular application, emergency, okay, once in a while, it's not so problematic, but systematically discharging batteries, the lead acid batteries that low is not advisable. In any case, we have the discharge, the number of cycles. For lead acid batteries, between 1,000, 2,000 cycles, okay? This is an example from the Hopeke, yeah? This is from the sealed batteries, the OPZ-V manual, and we can see the effect of temperature, yes? And the effect of the depth of discharge in the lifespan of the batteries, okay? For instance, we take the line on the top, the blue one, that would be a temperature of 20 degrees Celsius. And we can see that if we only discharge the battery down to 20% of its capacity, it can give us 8,500 cycles, okay? If we consider that one cycle, we do a cycle in a day, for instance, that would be 8,500 days of operation. Now, if we discharge this battery, same temperature, okay, if we discharge it down to 80% of its capacity, same battery, same temperature, it will only last for not even 2,000 cycles, okay? So 1/4 of it. Obviously, there is a relation. It's 1/4 in the number of cycles and 1/4 in the depth of discharge. So in the end, it is a matter of understanding how this battery will work, okay? And putting in perspective the durability, okay, the lifespan we want for a battery. In off-grid applications, mini-grids, remember, we're talking about remote areas, remote places. We're going there and changing a battery is not easy. Logistics are complicated and are very expensive. So it is not a bad idea to oversize batteries a little bit, okay? Not in the capacity, but in the depth of discharge. So preventing having to change batteries too often, okay? Okay, for lithium-ion batteries, well, essentially, as we said, and engineer Antolin also discussed with us, they are like a new generation of batteries for the solar industry. They have advantages, very clear ones. They allow for higher depth of discharge levels, down to 90%. They have longer lifespan, 4,000 cycles, 3,000 cycles, even 5,000 cycles. They have higher energy densities, better efficiencies, and they require less maintenance than the lead acid, okay? When we look at the discharge curve comparison, we can see that while lead acid batteries will have a bit a more constant drop in the voltage. Okay, this curve perhaps if we compare it to the Hopeke one would be a bit more flat, but anyway, we find a significant drop of the voltage once you exceed a depth of discharge of 40% in lead acid. With lithium ion, you can discharge and discharge and discharge very well up to 80%, and you will barely notice any voltage drop, okay? How does it work? It is in a, okay, similarly to the lead acid, we have the anode and the cathode, and there's an electrolyte, but in this case, the lithium ions are traveling, okay? Through the separator, and that separator is a membrane. It's not really an insulating material like we had in the lead acid batteries separating different cells, okay? In here we have traveling, we have a displacement of the lithium ion, the lithium ions from one electrode to the other, okay? And when it is a discharge process, we have the reverse trip, let's say, from the lithium ions, okay, from the anode to the cathode. So in a lithium-ion battery, we have a chemical reaction involving the movement of the lithium ions, okay, that are carried by the electrolyte. In lithium ions, typically we have graphite, yes, in the anode, and in the cathode we can have different solutions, different technologies, as we will see. Okay, so lithium-ion batteries, the different technologies, they mostly differ by the materials by which the cathode is built. Okay, is conformed, while the anode is normally built out of graphite. Okay, very quickly, what would be like a cut in a lithium-ion battery? The main differences, as I said, is that there is a separator, membrane separator between the cathode and the anode, and the electrolyte, instead of being a mixture of water and acid, in this case, it is a salt, lithium salt, yeah, dissolved in an organic solution. So less toxicity in lithium-ion batteries than in lead-acid batteries, okay, and less health and safety problems related to the electrolyte. That's another advantage. As I said, the different types of lithium-ion batteries, they depend on the chemical composition of the cathode. The most, well, practically the only ones we find in the solar market are the lithium iron phosphate batteries that are normally known as LFP, because the cathode is built out of a ferrophosphate, okay? Okay, this is the material for the cathode. And again, in the anode, we will have a graphite. And other types of lithium-ion batteries are these ones in the table, the NMC, which is the nickel manganese or nickel manganese cobalt oxide in the cathode, or just the manganese oxide, or a nickel cobalt aluminum oxide, or the cobalt oxide. Okay, so all of these are types of lithium-ion based batteries, but the difference is in the chemical composition of the cathode. And each of these batteries have, well, different properties. Okay, the reality is that for solar applications, according to what our colleague from Inventus Power, yeah, was recommending, the ferrophosphate type of batteries are the ones that have the highest advantages for solar applications, because they have lowest internal resistance, because they have a very high cycle life, yeah, the highest of the lithium-ion families, between 2,000 to 5,000 cycles. Yeah, compare that to the 500, 1,000 up to 2,000, if we are lucky, cycles that we find in a lead-acid battery. Sorry. And in terms of safety, yeah, they are the safer of them all. Okay, this is why the LFP batteries, ferrophosphate lithium-ion batteries, are the most widely found in the solar industry, on the solar market. Okay, for the advantages, I think we can skip this because we have already talked about that, depth of discharge, energy density. One aspect that was a little bit controversial, yeah, about lithium-ion batteries is the self-ignition, which in technical terms or in the industry, it is more described as thermal runaway, yeah. Well, this could be the main disadvantage of lithium-ion batteries, together with the higher cost. But the higher cost, in a way, it compensates with the longer operational lifetime, okay? So in this graph here, we can see the comparison of different lithium-ion battery technologies. And again, the ferrophosphate, the iron phosphate batteries are the ones that have better, or let's put it that way, they have less problems with the thermal runaway. Yeah, they burn less and they burn at much higher temperatures if they happen to burn. Okay. So again, the iron phosphate lithium-ion batteries are the best suited ones for solar applications. Yes. As a summary, let me go back to this very nice slides that engineer Antolin shared with us, with a good comparison of the different types of batteries we can consider for small applications, off-grid applications, solar PV systems. Yes, we have these first two are lead-acid batteries, the flooded or the open, cell type, or the sealed or the maintenance-free, type. With safety, important aspects: the safety, the maintenance, the energy density, the specific density, of course, for lithium-ion, between 3 and 5 times more than that of the lead-acid battery. The life expectancy, number of cycles, at least 3,000 for lithium-ion, maximum of 1,000, 1,500 if we are lucky for lead-acid. The costs, initial costs, but then we will need much less replacements with lithium-ion. Yeah. At the moment, the application of each type of batteries, the flooded open lead-acid batteries for small off-grid applications. I would say that now, these days, the sealed batteries, maintenance-free, are also becoming very much used for solar home systems and for small off-grid applications. Okay, while lithium-ion are more still a novelty for off-grid applications, and they are mostly used for industrial premises, for residential grid-connected backups, and for some mini-grids starting. Okay. Finally, a few comments. I already mentioned that, but storage is also valued in large PV plants. I'm not sure what is the situation of the storage in the Cuba plant that you have in Mozambique, but this is one aspect that we will get to discuss hopefully when we have a presentation with the colleagues of EDM about Mocuba plant and what kind of storage is there installed or previewed to be installed. Yeah, but in a nutshell, in summary, the storage will reduce the variability of the power output, yes, of the PV farm, and that is very much appreciated. Yeah, from the grid point of view, yes, it will smoothen the output of the PV plant in the event of a cloud, in a sudden reduction, yes, drop of the power plant production. The batteries can control the run rate, and imagine they have to deal with megawatts per minute, so it's not a small thing we're talking about here, to eliminate very quickly voltage and frequency fluctuations that can really damage and get the grid to become crazy. Apart from that, batteries can be very beneficial in terms of financials of the project, because power plants need to operate under some conditions, of voltage, frequency. If there is a failure or if there is a misperformance out of those thresholds, there can be penalties, there can be problems for the operator. So batteries are very helpful in that sense too. I invite you to check if you're interested in large scale or utility scale batteries. You can check this IRENA. This is the innovation toolbox, yeah, from the International Renewable Energy Agency. They are very recently starting, yeah, to discuss about these aspects. These aspects are relatively new, but becoming more and more important. Essentially, we can use lithium-ion batteries are very suitable for battery ancillary services related to PV plants and to solar farms, but also lead-acid batteries are suitable for some of the services that the PV plants may need, like the load shifting or the capacity reserve, or the upgrade deferral, spinning reserve, etc. So again, lithium-ion and lead-acid, together with other technologies that I didn't put here, like flywheels, sometimes, yeah, floated batteries, but very large ones. But again, the same technologies, lead-acid and lithium-ion, are, especially lithium-ion, are very much in consideration for large plants.